So for our last project in modern physics, let's take a look at quantum scattering off of the hydrogen atom. This works a little bit differently than the bound states. We're going to use a little bit different method than we used before. The picture you want to keep in mind here is that you have an incoming wave of electrons that are coming in from the left. They are moving in what's called a plane wave. So this e to the ikz represents sines and cosines that oscillate along the z-axis, which is horizontal in this picture. All these electron states are going to interact with the hydrogen atom here, and they're going to scatter off. They're going to scatter off in a whole bunch of different directions. We're going to measure those directions as this angle theta here. And so our incoming wave of e to the ikz is going to get modified by this scattered wave, which has this e to the ikr over r. This is what gives this wave its spherical shape. So e to the ikz gives you a plane shape. E to the ikr over r gives you this spherical shape coming off. That's going to get multiplied by this scattering amplitude f of theta. So basically, in a scattering problem, your goal is to figure out what f of theta is. Once you know what f of theta is, you know how much of the wave you're expecting to get at each angle in the outcoming scenario. So even though this is more complicated, even though this has some complex stuff going on, and it's a different picture, it's still obeys a Schrodinger equation. So it still has this second derivative of the wave function equals a negative value times the u, the q times the wave function here. This u here is a slightly modified version of the wave function. So instead of being just the radial part, it's r times the radial part. That just makes the math a little bit easier to set up. Here we're defining what Q is. Here's your energy eigenvalue like we had before. Here's your potential energy. Again, this is K E squared over R. And then here is the centrifugal term. You notice this is the same as we had before because this is the same problem as we were studying hydrogen atom, but now we're looking at scattering states instead of bound states. The scattering amplitude is built out of a few different pieces. The most important thing is this delta L here. This is what we call the phase shift. This represents how the phase of the wave is shifted between when it comes in and when it goes out. This has quite a few different pieces to it, so this is great for a computational study. This gives you a definition of what all these things are. The most important thing to look at here are these JL and NLs. These are what we call the spherical Bessel functions. These are a two-dimensional analog of the sines and cosines. I happen to be wearing those on my shirt today. And so these things oscillate up and down with this decaying amplitude. They're given by this summation over derivatives of sine of the argument divided by the argument. So these are things that you can compute, but again, like we did before, it's a lot easier to work with these things if you just import the Bessel functions from the NumPy library. So what we're going to use here is something called Numerov's method. This is something I am just now getting into. It's a really cool approach. It's a complement to the Euler-Kromer method that we usually use on this channel. Basically what it does, it takes advantage of the fact that there is no first derivative in this equation. Right? There is no u prime in this differential equation, and that actually makes the Numerov's method more accurate at larger step sizes. So what we're going to do, just like we did with the shooting method, we start off at a point far to the left. We set u equal to 0, just as an easy way to start. And then we step forward in steps of h. Basically, you're going to go from u0 to u1 to u2 to u3, etc. And we update those u values based on this recursion relation here. It requires knowing the current value of u and the previous value of u. So we're looking at the step we're at now, the step we were at before. We're taking those two steps and combine them to get the next step that we're at. A little bit reminiscent of the Fibonacci series, right? You take two things, add them together to get the next one. It's just got a whole lot more to the addition there. But it turns out this thing is accurate to an order of your step size to the 6th power, which is a great improvement over the Euler-Kromer method that we typically use. If you would like to see a derivation of this, I've got links for you here in the notebook. I don't really feel the need to rehearse that with you here today. Let's see, so we come down here. Here is where we define the Numerov method. So this has the same form that we had above for that u. Next, we're looking at So we're looking at one value, we're looking at the next value, and then we're looking at the value 2 values from now. So So in order to get U2, we need U0 and U1. In order to get U3, we need U1 and U2, etc. So this is just setting up that same recursion relation that we had before. Here we're bringing in those special libraries. Here we're bringing in the spherical harmonics because I do not want to calculate those by hand. The potential energy we're going to use a little bit different than we had before. Here is your 1 over R for the Coulomb potential. We're going to modify this into the Yukawa potential energy, which tacks on this e to the negative r over s, which screens the potential energy. So it's taking that potential energy and it's making it die off a little bit as you get closer to the origin, which is really great because we kind of need that. Okay, so here's the Yukawa potential. I'll let you read about that in the link here. We come down here. Here's where we calculate that Q to get us our differential equation for the Schrodinger equation. And here's where we calculate the wave function, right? So we just take the Numerov's method. We apply that to get the wave function here. Then we simply return the wave function here. And we come down to here where we're actually doing the computations. All that was a nice setup. Finally, we come down to the code cell that does the actual computation, that actually runs the thing. This is the thing that's going to calculate those phase shifts for us here. So what you'll find here are the phase shifts that we're calculating in this x value here, and we're saving it in this PS array. So this PS array stores the phase shift values. Then what you're responsible for doing, you're responsible for taking these phase shift values and using those to calculate sigma, the scattering cross section. You're going to do that using the equation for sigma up here. So your sigma of theta is equal to the modulus of the scattering amplitude squared. Scattering amplitude you're going to get from this equation over here. So we take the phase shift, turn it into the scattering amplitude F. So let's review where that happens. Yeah, so here you have this FL. This is the L scattering amplitude piece. So your sigma is just going to be this thing squared. Nice and easy. So next comes the visualization part. This is going to show you the actual wave function U. This is the thing that we were interested in calculating. Here it is versus R in units of, in atomic units. Come down here, we graph the delta L values. These are the phase shift. You notice they're going to die down as L increases. And finally, we come to the scattering cross section. This is the thing that you calculate as a function of theta. It should be highest at 0, where the thing is spitting out this way, and get lower as we rotate around. Just like we saw, I mean, we're back to scattering like we had in an earlier video, which is pretty cool. So that'll bring our modern physics series to a close. I want to thank you so much for watching. This is a fun class to teach. It is a great opportunity to learn about so many of the weird things in physics. I would love to hear about your experiences in the comments below. Thank you so much for watching. I will see you next time. Bye-bye. Thank you for joining me for this journey through modern physics. If you enjoyed this series, there are plenty of other videos on this channel to help you continue your exploration of advanced physics topics. If you really enjoyed it and you'd like to get notified of when we release more videos, hit that subscribe button below. We update this channel with new physics coding tutorials every Monday and Wednesday, and we would love for you to join us.